Good evening, everyone. This is Celso Batalha, and, uh, and welcome to Astro 10, the online course. And today we are having a midterm, and just oops. Oh, Armando is there, and Maria Mandujan is there. Let me stop taping. Do you guys have any question? Kind of a particular question that you don't want to share with everybody else? If you do, I will stop taping, and then I will not start taping again. I think Amanda had a question, but I don't remember well. No? Let me see if I can get the chat going on. Probably not. And I have my microphone on. I have my video on. I have the impression that one of you want to ask something, and that's what's the reason you came here. But I might be wrong. Nope. Okay. So so if you want to ask anything, just jump in and use your microphone for that. But let me stop my mail. Just a second. Okay. All right. I think now we are on the go. So there are three major things going on. One is the midterm. We have a midterm today, and it's the first midterm. We have others coming up. We have a total of three midterms. But what I will do, I will open this midterm again, but it's not going to be the same questions. But I will have this midterm open again. And today is Thursday, this Saturday. So Friday is going to be probably a day you might want to review the class, and then on Saturday you take the midterm. And the questions will not be the same, but the idea is there. You might find some of the questions being the same, but not necessarily. Okay, so Saturday, and the way it goes, you do the midterm again, and I will pick up the highest score, of both attempts. So nothing to lose, except an extra hour on Saturday to review astronomy. That's one thing. So midterm is going to be available today, in fact tonight, up to midnight, and then it closes. So, and that gives you some idea how these midterms work. I mean, we have the entire day to do the midterm, but you cannot. You have to complete it during that time frame. So you have to make sure your computer is up running, you have a good internet system, and you're not using some device that might crash, or something might be funny. So make sure you are well covered. So the next attempt is going to be on Saturday. Okay, that's the first thing. Do you guys have any question um, regarding the midterm that you want to ask? Nope. Okay, the second thing is with respect to Stellarium, and I'm not sharing my window. Let me show my window to all of you. Okay. Let me share the window now. Share screen. This one. So the Stellarium is a software. I think one of you, at least I know, it has a software running in your machine. I think Amanda, if I'm not mistaken. And so it's a software. It display what's going on in the sky, and you can choose. You can choose daytime. You can reset in such a way that you can see things nicely going on or not. For some reason, I have to reset my entire Stellarium. It's giving all too much information here. But I had some students that couldn't complete Stellarium last week because of I don't know. Either they didn't invest time downloading on time, or something happened. So I'm extending Stellarium for another week. Though the Stellarium that closed, I'm opening again and extended for 1 week. But I can't do this all the time. So I'm going to do, just because it was the first submission on the software. And this week we are running with a discussion, and I apologize, I haven't been gone there yet, but I will, probably tomorrow, I will read the discussions, and if you had posted anything in there, I will reply to you. And I will also try to create another discussion over the weekend, because I have some upcoming discussion that is still open. So that is my point on Stellarium. If you have any problem in opening, just talk to me. And the best way to do that is either going to my face-to-face office hours, or here. But in a chat room like that, you have to be able to use a computer that you can share your screen, so I know what the problem is. Otherwise, I can't help you. All right. So either office hours face-to-face, or you in this chat room, make sure you have a computer that you can share. You cannot use a cell phone because Stellarium doesn't go to your cell phone. You gotta be in a computer. So any question regarding Stellarium? No? Yes? Maybe? Okay. Midterm, Stellarium, third one. The third question is with respect to the moon observation, and I just realized that a video that I did with explanations didn't come up. I mean, it really didn't show up. What?
Can I use your credit card to buy my homecoming ticket?
Yeah. So I will check. I just see this before. Before I know one student had mentioned that she attempted um, to see the explanations, but I went to an old video that I posted. When I say old, it's 2 or 3 weeks ago. And the video was there, but the most recent one, it's not uploading, and I have to figure out what's going on. Okay, so I would check that. But basically, what you do, you have to go out and observe the moon. For instance, today is a good day to start. So if you go outside, you should be able to see the moon in your western sky. Why don't you two do that? You want to do that? Can you see your western sky, Maria and Amanda? Can you go there and take a look? I will do that. So just wait. I'm gonna go to my window, and then I'm gonna look west. Let's see if the moon is there. Just a second. And sure enough, so now is 7:14, and the moon is right a little bit past south, like you can see over here. And in respect to horizon, is about, so I make in an explanation that I did in a video before, if you make a fist like this and hold the fist at arm's length like I'm doing, so this fist projects about 10 degrees in the sky. So what I did, I saw the moon a little bit past meridian, like I'm seeing here in the software. And then what I did, I imagine a plane that passed through my eyes and go all the way to infinity. Then right there, I see my fist. See that? So I'm putting my fist here. So this is 10 degrees. 10 degrees right here is 10 degrees in the sky. 20, 30. So I saw the moon about 30 degrees, between 30 and 35 degrees above my horizon, and a couple of degrees or so off my meridian. And the meridian is because one of the trees, I know that tree is facing south, is in my south direction. So did you guys go outside? No. Are you guys there? I don't know what's going on. It's so funny to talk to a mute audience. Oh, I can't share. I'm sharing my screen. So then let me show you what you should do next. So the explanation that I put in that video, and I will show again. Let me stop sharing this. And let me get a white page. Get a white page. You guys should go to the window. Let me prepare this page. And meanwhile, go to the window or to a place you can see your western sky, south and west, and see the moon. You have a waxing crescent moon right there, beautiful. Okay. So the explanations goal in this moon assignment is pretty much like this. You take on a piece of paper like that, you draw a line with a ruler like that, put a ruler. And on your left-hand side, you mark your eastern sky, and in your right-hand side, your western sky. And then this is pretty much your due south. So in my case, as I saw the moon now, the moon is 10 degrees. So I make a scale here, beginning on the south and going all the way up. So the moon is 10, 20, 30. This is 35, 30, 40, 50. So 10 degrees, 20, 30. All of that should be done in scale, 40. So I saw the moon about a couple of degrees off south. So which means this is 10, 20 towards west, 30 degrees towards west, 40, and then I have negative 10, so it's kind of a towards east, right? This is negative 20, and so on, so on. So I saw the moon somewhere here, and the moon is pretty much like this, a crescent phase, okay? And then in this paper sheet, I draw this scale, this axis, and I also mark the time I did the observation. It was 7, I don't remember what, but let's say 7:14 p.m. Okay. So what I do next is 1 hour from now, which means at 8:14, I would go out in the same spot that I observed the moon, So in my case, I did from my window, but I could choose the door outside. I could go to my front yard. I could go to the street, or I could go to a place as long as it's safe. And I stand on the same spot that I stand at 7:14. So I cannot be off. If I'm off, my references will be gone. So right here, due south, I have a tree that I use as a reference, and I had some landmarks that I could even mark, on my drawing. I'm not a good artist, so you have to forgive me for that. You might have some post line going there, with cables, or you might have some house somewhere in there in your eastern sky. So you do that kind of thing. But 8:14, you go back and observe the moon again. And where the moon is going to be? It's going to be in the same spot, or it's going to be here, or it's going to be there, or it's going. And which phase are you saying? Is the same phase or not? And then let's say you observed here, and the phase is not crescent, but is a gibbous phase now. So you observe here, 1 hour from now, right? So then you mark 8:14, and this is October, by the way, October 6th. And this was in October 6th. So first observation, second observation. The third is going to be done at 7:14, but October 7th. So in this sketch, where should you place the moon? Should you place where? So you have to go same spot, rest on the same spot, find the moon where it is, and then mark, use your fist at arm's length. One finger is about 2 degrees. This is about 2 degrees in the sky. So at arm's length, a finger, the point of it, the tip of your finger is a good, choose the proper one. So it's about 2 degrees. And then you can use this to scale and place the moon in the sky. So you did the first observation, you did the second, the third. I don't know what the moon's gonna be. Let's say the moon's gonna be there, and the moon is full moon. I don't know. I'm just making up. And then you mark October 7 at 7:14, and then you repeat the observation 7 days from the first day. So that should be October 6, 7, 8, 9, 10, 11, 12, 13. So 1 week later, October 13, where the moon's going to be. It's going to be here, this, or that. Okay. So once you set this sketch done, and I would recommend that you start tonight, but now it's late, but you can start tomorrow. Tomorrow is a good time. So if you start tomorrow at 8 o'clock, is perfect. And then you're pretty much done. Okay. And then you have to answer questions, and the questions are given. Let me show you where. So if you go to your course, in the first module of your course, which is this one, in the first module, general useful links, you have a link to moon observation. And once you click that link, it's going to take you to, I'm not sure if you're still going to see it. I just click it, and then it opens a link to where the observations is shown. And then you can do your observation. Let me show you the link. I don't know if you're seeing right now. And here it is. Okay. So here start with basic explanations on how you should start and organize the meeting, and then I have discussion questions that you have to answer. So you add the sketch you made, and you answer these questions, and you give it to me. You can upload that information up in Canvas, and then you correct. The due date is December, and then you're done. Now, let's say you cannot do this observation for some reason, right? So what you can do is to go to one of our public viewings, and we have one tomorrow at Montgomery Hill Observatory, which is in Evergreen Valley College in our campus. So you can go to the campus, and then the viewing starts at 9 o'clock, and at 7 o'clock we have a talk. So you're supposed to submit a report of what you learned in that talk. That goes from 7 to 8. The talk's going to be about Pluto as a dwarf planet, and it's going to have a lot of information about some of the objects in our solar system, and it coincides with what we're going to be learning next week. And pretty much you go to the observatory, and then I will hand you out a observing log, and then you have to fulfill and complete some observations, and then you have to submit that to me and present a report. So either way, you have 2 reports to do tomorrow, or in the talk we have. So you can either go tomorrow, or you can go November or December. We have 2 other stargazings this semester. So it's 2 chances. So I would like you to go to the stargazing anyways. But if you go to get part of this assignment done as part of the course, then that's great. So you go there, have a good time, and do assignments. But you can not do the assignments and complete the moon observations at home or in your workplace. Okay? Good enough? Okay. What I would like to, Amanda, do you have any question? Okay. So what I would like to do is, so I talk about stellarium, I talk about midterm, I talk about the moon observation, and now I'm going to highlight the topics of next week, which is pretty much terrestrial bodies, about terrestrial objects. And so let's go over that subject. So terrestrial worlds are worlds in our solar system that are rocky type. By rocky type, it means they have minerals, they have carbon in there. They are not primarily volatiles, made of volatiles or light elements. So if you look at Jupiter, Saturn, and Uranus and Neptune, most of the material in its planets are light elements, hydrogen and helium primarily. Okay, but if you turn your eyes and then you look at terrestrial worlds like Mercury, Venus, Earth, Mars, the Moon, the asteroids, they have a different chemical composition. They are more rock type. They have silicates. They have oxygen, and oxygen embedded in rocks, and not a lot of hydrogen. So hydrogen can be found in water, but that's it. And in some carbonic compounds, organic compounds, but pretty much that's it. In Earth crust, most of the elements, the most abundant elements on Earth crust are magnesium, aluminum, potassium, sodium, aluminum, magnesium, iron, potassium, sodium. I have to write down silicon and oxygen, and I think I'm missing one. But see, you don't have hydrogen and helium. If you go to the universe, as we know, the most abundant elements in there are hydrogen and helium. Those 2 elements primarily make all the stars we know. and then you have trace amount of the rest of the chemical scale we have. But here on Earth, the terrestrial worlds, they are different. And why is that? So to answer these questions, we have this chapter, why in the solar system, when you look at our solar system, so these objects near the sun, they become terrestrials. And objects that are further out, they are more kind of a Jupiter-like, they are more kind of a hydrogen and helium-like objects. And also we are going to study in this chapter some of the main features associated with the terrestrial worlds. In particular, in our planet Earth, plate tectonics plays a major role in controlling the landscape, in shaping the landscape. Plate tectonics is a theory that is able to explain why we have volcanoes and why we have earthquakes and why we have the mountains we do, why we have the canyons we do, all because of this constant motion of 12 or more major plates that rest on what we call Earth mantle, which is one of the interior regions of our planet. So these plates, they are resting on the mantle, and because the mantle is constantly undergoing convection, of course, it takes a long time to complete a cycle, but because of that, the plates, they move. So sometimes they move past one another, and then we have earthquakes, and we call San Andreas is one of these example of plates that pass one another. And we have divergent plates, and in regions where divergent plates take place, water fills in, and then we have oceans. In some other places, the plates collide with one another, and if one of the plates is heavier than the other, denser, it slides under, and we call that phenomena subduction. And as a result of this subduction, liquid rocks bubbles up, creating volcanoes, and then we have chains of volcanoes like in north of United States. We have the Cascade Range, which is the result of Juan de Fuca plate colliding with North American plate. And also we have situations where two plates collide and they have the same density, and as a result of this collision, big mountains are formed, like Himalayas. That's one example. Okay, so let's go over and browse through these slides. Terrestrial worlds, Mercury, Venus, Earth, Mars, and the Moon. And here's a table that gives you some numbers related to these worlds, to these objects. One of the numbers I would like to call your attention is right here. One is the mass in respect to Earth mass, right? It's 1. So you see Mercury is less massive as Venus, less mass than Earth, and all the other objects are less massive. So Earth is relatively the most massive among these terrestrial worlds we are talking about. And the other one is density. Density, it gives you some sense of how much material one object has with respect to a fixed volume. For instance, you take an envelope, right? An envelope, like one of those pony envelopes, and in one of it, you put nothing inside. You just pretend you put some air in there and then close it, and you have kind of a, kind of a bulging. And then in another envelope, you put a lot of sand in there, right? So the volume is the same. You take the two envelopes and then you show, they look about the same. But when you do hefting tests and you hold both of them in each one of your hands, you notice that obviously the one with sand seems to be heavier, right? And the one that doesn't have sand is kind of a lighter. So density is a quantity in physics that gives you the ratio between mass and the volume that mass occupies. So if you look at the density here, the most dense object you have in the scale is planet Earth. And then the next one is Mercury, and then Venus, and then Mars, and then Moon. So it's about 3.3 or 3,000 in the case of the of Moon, 3,340 kilograms per cubic meter. And by comparison, water is just 1,000 kilograms per cubic meter. So what does it tell us? Well, it tells us if you take a scoop, an average scoop, you take a scoop of these terrestrial planets and same volume, right? And you take a scoop of same volume of water and then you hold it, if you could, in your hands. So Earth would be the heaviest one, and water would be the lighter one, right? So you can use the density, and you can calculate density using Newton's laws of motion. So you can use the density to probe what type of composition, chemical composition, these objects have, and by doing so, you can certify that's. I mean, they have some different chemical composition, and the terrestrial planets are denser than the lighter planets, Jupiter, Saturn, and Uranus, and Neptune, and all of those guys. Okay. Now, because they are terrestrials, because they have the rock surface, they still have the remains of ancient collisions that happened 4 billion years ago or more, or more or less, on their surface. And by looking at these impacts, you can probe the past history of our solar system. Okay. So impact craters, we don't have a lot of impact craters that we can easily see here on Earth. We see them easily in the moon surface, and if you go to the observatory tomorrow, you should be able to see it. But if you look at Mercury, if you look at Mars, more or less, if you look at Moon, you can see abundant craters. There are an abundance of craters, and the reason is, so although our planet Earth and Venus, these terrestrial planets were formed at about the same time, 4.5 billion years ago, along with the Sun. So these planets, they went through different historical phases. So our planet Earth has two things going on that helps to erase all these craters remains, and one is hydrologic cycle. So we have a hydrological cycle on Earth that rains fall down some mountains, and then this rain it rains down all the way to the ocean, and as a result, this erosional process erases indications of craters. That's one example. Also, we have plants. Plants erode and use and exert chemical exchange with the soil, and then the records of these impacts are gone. But another important factor that contributed to erase any remains of craters here on Earth is plate tectonics. So plate tectonics, let me see if I have a picture coming up here. Plate tectonics. I have everything minus plate tectonics. There you go. So plate tectonics is this. So we have this lithosphere, broken pieces, right? And these pieces, they move. Now, in this example here, the two plates are moving apart, right? And as a result, water fills in, and then we have an ocean. But you might have situations like here in North America, right in this region right here, Juan de Fuca. So this a small plate collides with the North American plate and undergoes subduction. Let me show you. There is a good animation here. Let me go there and show you. Let's stop sharing this. And let me bring that animation. I hope this you have just a second. is a nice example of tectonics. It's coming up. Huh. Why I'm not getting? For some reason, it's not opening. It's not opening. Why is that? Oh, Windows only. It doesn't run on Mac. Oops, sorry. Plate tectonics is in Fat, Colorado. It's a great simulation. Um, yeah, sorry about that. If you want to play with it, let me copy and paste the address. It's right here, but it's only for Windows. That's why it's not coming. And I put right here in the chat room. Right there. So I put the link in the chat room. But plate tectonics, and I think, let me see, you have to go back here and share the screen, right? There you go. So yeah, so plate tectonics is this major theory that explains it all, and you have a data. You can measure the plates moving few centimeters. The rate in which your nail grows every year is the rate in which this plate moves. So pay attention to that. So Earth has plate tectonics. So if you have a big chunk of lithosphere full of craters on it, so eventually, because of subduction, this plate just slides under another one, and all old craters are gone. Most of these major craters were formed pretty much before 4 billion years ago, in early ages than 4 billion years ago, and by 3.8 billion years ago, most of these major collisions have ended. So you still have some impact. So we have here impact on Earth, but not as much as you used to have. So craters, if you happen to go to the observatory to model, and the moon is going to be there, it's going to be nice to see. Young craters, those that are more recent, they don't show a lot of signs of erosion. So the edges are still sharp and crisp. You have a central peak on them. They don't have a lava flow floating the basing of these craters. So there are several indications of the youth of these craters. Now, in terrestrial worlds like Earth, earthquakes, in our case, earthquakes are a result of plate tectonics and interaction. But earthquakes have an importance because when these quakes occur, it generates seismic waves. And these waves propagate through Earth, not only surface, but also through the interior part of Earth. And, um, and when waves penetrate Earth, the Earth interior, they change direction and undergo what we call refraction. And by the same way that light, we studied in chapter 4, when light penetrates a piece of glass, undergoes refraction. So the seismic waves also change direction as they go in Earth interior. And geologists can study the propagation of these waves and the different types of waves involved in this propagation, like S waves, P waves, surface waves, and they can create a model for Earth interior. And then model tells that Earth has a core, has a mantle, and has a lithosphere. So basically, Earth core consists of an inner core that is primarily made of iron and nickel. So when Earth was formed 4.5 billion years ago, Earth went through a phase in which was completely melted. And the heavy atoms, most of it sank to the core of it. Like if you go to the store and you buy a bucket of ice cream cookies with little ice cream with chocolate chips, chocolate chips and ice cream, let's say vanilla. And as you go home, you stop the car and your neighbor that likes to talk a lot come talk to you. And then stay talking, 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 talk, talk. The ice cream melts. And what happened with the chocolate chips? It all sink to the bottom, right? It goes, gravity brings all the way to the bottom and concentrate there. So the same thing happened with Earth, with iron. So iron, nickel are heavy atoms, and they are abundant in the solar system. So they all sink down to the very core, and the mantle, although it has iron, it doesn't have as much as in the core. So these light atoms, they stay afloating on top. So it has an inner core that is pretty much solid inner core surrounded by an outer core that is liquid. And on top of it, a mantle and a crust. The crust is brittle, it can break. The mantle is plastic. It's also solid, but it's plastic. It can undergo motion. That's why we have the convection, that is the belt that moves the plate tectonics and provides energy to the plate tectonics. Let me see what else is interesting. Tidal forces is what is the result of interaction between Moon and Earth. It goes twice on Earth. High tides and low tides happen twice on Earth because in a period of 24 hours, Earth undergoes almost a full rotation, and the part of Earth that is facing the Moon is the one that is going to be bulging as a result of gravity, and this bulging occur in opposite sides, right? So the gravity is intense in this part of gravity is intense. Let me get my annotate. Gravity is intense here. Oops. There you go. Gravity is intense here and less intense there. So basically, this part is stayed behind in respect to this one that is pulled and is stretched towards where the Moon is. In fact, if Earth were not rotating, I'm exaggerating here, okay? if Earth were not rotate, this is Earth, solid Earth, and this is water, and this is water. So if Earth didn't rotate, this bulging part would be facing the moon. But since Earth rotates, this bulging part moves and goes away on a small angle here. With respect to Earth. So the bulging is not exact. So a high tide is not exactly when the moon is crossing meridian, right? It's a little bit off. Uh, I got a freezing window here. What? This happened before my window. No, I don't want to mute. Okay, let me see if I can go back here. I will stop sharing because something. Sorry about that. Let me go back there. Yeah, I got in a loop here. Okay. Earth has magnetism, and this magnetism comes specifically from the part of Earth interior that is melted, the liquid core. The liquid core contains ions, and as Earth rotates, these ions generates this global magnetic field. And you all know because you have playing with the compasses, especially if you were Girl Scout or Boy Scout, and that's it. So we went through plate tectonics. The volcanoes are the result of it. Moon went through volcanism as well, although the moon doesn't have volcanoes as so prominent as the ones we see on Earth or in Mars or in Venus. But the moon had lava flow during its early formation. And here you can see indications of flow right here. So it's being shown right there. Let me see if I can get it right there. Yeah. So it's a nice chapter. It's a complement of star formation, and the reason why, and I would like to stress that the reason why terrestrial planets and terrestrial worlds they happen to be solid and rocky is because of the sun itself. The sun and its radiation and its heat swept away and cast away the light elements from its neighborhood. So closer to the sun, it remains, first of all, the heavier atoms, and the lighter one interacts with solar wind and solar radiation, and were taken away to regions where Jupiter and the Jovian planets are located. And those planets start just to add on to their system these lighter atoms and gases. And the metals, the metallicity became more concentrated in the regions closer to the sun. So if you look at Mercury, Mercury is more metal rich than Venus, which is more metal rich than Earth, which is more metal rich than Mars, right? So you have this degradation or degraded concentrations of metallicity as you go from Mercury all the way to Mars, because these planets were formed at different distances from the sun. Okay, and that's pretty much it. that is pretty much it. And any question, Amanda? Okay. All right. Good night to all of you, and thanks for coming, and thanks for watching this. I will try to upload as soon as possible, and I try to figure out why that moon video is not showing, and I will fix it. Good night to all of you.